Video, we're going to be going over the main challenges of machine learning when it comes to particularly giving in data to a machine learning model and what are some areas that we can improve on. Now, this is not going to be particularly going over the algorithms behind machine learning. It's more going over the input data that's going in. This is tutorial number 4 of our machine learning series. In the last tutorial, we went over different ways of training an AI model, particularly when it comes to generalization and how model-based learning versus instance-based learning can work when it comes to training an AI model. In today's lesson, we're going to be talking about some of the main challenges when it comes to the particular training data that you are using. So let's go ahead and start off with the first challenge. The first challenge would be an insufficient quantity of data. So basically when we don't have enough data. For a machine learning model to recognize new instances coming into the training, recognize new instances and compare them to the existing training set, it needs thousands of millions of examples potentially, especially if it is a much more complicated process. And so the amount of instances in the training set does determine the accuracy of the model. In fact, there was a paper actually published in 2001 that went over different ML models, so different algorithms here, a memory-based Winnow, a perceptron, and different ones here. And it was from 2001. But what this basically this graph is showing is it's showing that with these different ML models, that the accuracy of these models is equivalent when we give it a large amount of data, even though they're basically different algorithms. Now, you do see some variations, and that variation is expected, but you're seeing that the degree of accuracy goes extremely high, even if the algorithms are different, just because it is given enough training data. And so this is really showing how much important a sufficient training set of information is. And so you definitely need a large amount of training set in order to have a good model output, even if the model necessarily isn't as good. And so the people who wrote this article said that these results suggest that we may want to reconsider the trade-off between spending time and money on algorithm development versus spending time on its corpus development, in that the training set, spending more time on training the algorithm compared to actually building the algorithm. That being said, however, if most ML models are only given small to medium size data sets, and so therefore the quality of the algorithms being employed is still a very heavy factor that influences the accuracy of the model. And so it is still important to understand that the accuracy of the model must be improved in terms of the algorithm itself, but the training set of information, especially when you're extrapolating it to very high numbers, is very important and very influential. And so a sufficient training set of information is very important, regardless of the algorithm. The next thing is a non-representative training data. So remember, we need to generalize from a training data. If we are giving a data that is not very representative of an overall population that we are trying to generalize to, that is not very helpful whatsoever. And so when there's really two problems that we can face here. One of them is sampling noise, the other one is sampling bias. Sampling noise occurs when the sample is too small and makes the data unrepresentative of a larger trend. And so basically what this is basically we're using a way too small sample size, and we need our sample size to become bigger so that way we can generalize in a larger group, right? Sampling bias, on the other hand, occurs when the sampling method itself is flawed. And so let's say, for example, you're conducting a poll, and the way you're conducting the poll, let's say, for example, is targeting particular individuals who are more likely to lean in a particular direction. In that case, even if you have a very high sampling, your sample size is big, there might be a sampling bias because the way that you're conducting that particular poll, let's say, might be invalid, and it might be resulting in a shift towards a particular group. And so in that case, your sampling method is flawed. There's another case where your sampling is too small, and that's sampling noise, and that results in it being unrepresentative of a larger trend within the data. And so we see a picture here. We see GDP per capita, and we're comparing it to the life satisfaction there on the y-axis. And if we just take a look here at a very small data set, we can kind of generalize, the algorithm can kind of generalize and say, hey, we have an upward trend that as the GDP per capita increases, the life satisfaction of particular individuals within that particular economy increases proportionally. That being said, when we add in more instances into our training set, what we see that is not always true. Even economies with a higher GDP per capita might not be necessarily having a proportional life satisfaction as we would have gotten had we only used the previous data. And so we need to obviously be able to generalize. In order to generalize, a powerful thing is to include more training sets. And so in this example, sampling noise may have resulted in a incorrect trend line that we are observing in the scatter plot. And so we need to make sure that we're avoiding those two things and making sure that we're able to generalize appropriately. The next thing that we need to understand is poor quality data. Poor quality data occurs when the training set is full of errors, outliers, and or noise. So we talked about sampling noise there. Again, the system has to be able to detect underlying patterns in the training set. And this is particularly true when it comes to model-based learning, right? Model-based learning. We talk about instance-based learning and model-based learning. This is particularly true when it comes to model-based learning when we're trying to detect particular patterns in the training set. How can we fix this? Well, we can fix getting rid of some of this noise and outliers by removing or discarding outliers from the training set. And if certain instances in the training set lack certain features, we might want to fill in these missing features or remove those instances from the training set. And so in that particular case, let's say you were to have instances of, let's say, the price of a car. And there are particular predictors that we can use in order to determine the price of a car. And let's say we're using a supervised learning model. Well, in that particular case, let's say we gave a car that has a particular mileage and a particular age and a particular brand. And based on that information, the AI model is going to predict what the price of the car is. And what we're going to do in order to help the AI model predict what the price of the car is we're going to feed it with a lot of information, with a sufficient training set. Let's say for certain instances that we're feeding into the algorithm in the training set, we are not including certain factors, such as, for example, the age of the car. Let's say for certain instances that we're including in our training set, we're only including the brand of the car. If we're only including the brand of the car, that is going to result in errors. It's going to result in incorrect information. And so what we can do to those instances is we can add in those missing attributes, or we can completely remove those instances from the training set. And so those really are two options there. Really two options there when it comes to that. So you got to consider poor quality data. And again, much of this is actually intuitive when you think about it. But we're going to get into some. The first chapter is more of just general knowledge principles that almost anybody can learn. I believe that as we continue on in this course, we are going to go into more like Python code and things like that, and we're going to get into importing particular libraries. We're going to get into TensorFlow and things like that. I probably am going to release like a full, maybe like 1 hour or 2 hour tutorial over the basics of Python or something like that, just like a refresher course. If you haven't done that already, in order to continue like later on with this course, you need to have like a fundamental understanding of Python in general, how to import libraries and things like that. So I will be releasing probably like a 1 or 2 hour tutorial, basically going over all the basics of Python, lists, dictionaries, tuples, looping, file handling, importing modules, using modules, becoming very good with Python is very important to continue on with this course. And so I probably will be releasing a tutorial very soon going over those basics. And you probably will want to install something like VS Code or something like that as we continue on in this course. But that's why the information that we're learning right now is probably pretty intuitive. But it is necessary information, and it is information that you would be expected to know. So make sure you're following along with this as well. So we covered poor quality data. Let's continue on with irrelevant features. So we need to remove irrelevant features from our data set. And we'll get into this more a little bit when we talk about overfitting the training data. But for now, just take it as it is, and then we'll hit back on this irrelevant feature section when we get into overfitting the training data. But we need to discard irrelevant information. This is called feature engineering. I believe we did something similar to that before. So there's two methods of feature engineering. One of them is feature selection. Select the most useful features to train among the existing features, and then feature extraction. We covered this before, combining many features into one feature through maybe via a dimensionality reduction algorithm, where we basically take two features. I believe in the example we gave in I believe our first or second tutorial, we talked about how we can combine the age and the mileage of the car into one feature, and that's called feature extraction. And we use a dimensionality reduction algorithm to get that done. And so basically combining many features into one feature will make the ML model faster. And so we use feature extraction there. All right, with that idea in mind, keep that idea in mind, and we'll put a pin on that and then come back to that later. But let's talk about overfitting the training data. This is overfitting the training data. We're going to spend a little bit of time on this. Overfitting the training data occurs when the model performs well in the training set but lacks the ability to generalize appropriately. And so we see here a graph here, and we see that we have a training set of information, and we're noticing here that up until it reaches roughly about 5,500 or $55,000 in GDP per capita, it is very accurate. But what we see here is that this model has the inability to generalize and extrapolate to larger x values. As we're seeing here, we're seeing that its life satisfaction is varying and it is not being able to generalize appropriately. And so this occurs when we're overfitting the training data. So the training data, this can occur for several reasons. The training data can be too small or have a lot of sampling noise. Maybe in this particular instance, we're seeing here that we gave many instances. Maybe it might have been a better idea to give less instances at the beginning and give more instances as we continued on, right? As we continued on, and maybe put the distance in between each of these spaces in terms of the x direction, make these distances bigger. So that way we could generalize it appropriately. And so maybe we need to make the training set bigger. Another one is feeding unnecessary predictors or factors into the training set. One of the examples that we gave here is, let's say the model is looking at this graph, and let's say right now, basically the only factor that we're giving in is the GDP per capita as a as an X value. But there might be features that we might be giving too much. So for example, let's say we gave the name of the country, and let's say countries that generally speaking at a high GDP per capita began with the letter Z. Let's say, does that mean that every single country does that mean that we can generalize that statement and say countries which start with the letter Z have a high GDP per capita? Obviously not. That doesn't make sense from any logical perspective, right? And so because of that, we need to eliminate factors that might be irrelevant. So getting rid of those irrelevant features can prevent overfitting the data. Okay, so that's an interesting scenario to look at. What are some solutions to overfitting training data? Well, one of them is to simplify the model by selecting fewer parameters. So this is actually very important. If you're giving too many degrees of freedom, if you're giving too much information to the model, then that might result in it developing, noticing a trend where a trend shouldn't really exist, and that might result in it generalizing in a bad direction. So it might notice a trend in one direction where a trend that doesn't exist. Going back to that idea of the starting letter of each country. So that's not good. Gather more training data is another way. We also should reduce noise in the training set. So again, this is talking about reducing outliers, reducing errors. Remember, noise is when we have a very small sample, and what we're trying to do is we're generalizing too much from that. Which will obviously reduce outliers. Anything that's an outlier, we can use an anomaly detection algorithm. We talked about that before in order to get rid of those outliers. So when we're talking about this, regularization is an important concept here in terms of getting rid of the risk of overfitting the training set. So being able to generalize appropriately. We'll talk about this in the next lesson with a hyperparameter. But basically, taking a look at the example here, oftentimes this might even be, for example, we talked about an example where we give fewer parameters. We might want to give more parameters, right? Because, for example, if we give too few parameters, then we might develop a linear model of a graph where we actually want a polynomial model of a graph. So, for example, let's say we had the equation y equals mx plus b, the slope-intercept form, and the only degree of freedom that we gave to the model was that it could change the m part of the algorithm and not the b part of the algorithm, the y-intercept part of the algorithm. Well, that might generate an unrepresentative result. And so what we want to do in that particular case is give it a greater degree of freedom. So giving it more degrees of freedom is important. And so allowing it to select more specifics might be helpful there. So the amount of regularization can be controlled by a hyperparameter that is a parameter of the learning algorithm itself. And we're going to discuss that in the next lesson as well. We're going to go very much in depth into the hyperparameter as well. All right, so that's regularization and the hyperparameter. So we'll get into hyperparameter a little bit later. This was more of a simplified explanation, but we'll get into hyperparameter and how we can generalize the information appropriately. Really, this information about generalization is very important.